So, everyone, welcome. Thank you for joining us today for this series of talks that's organized by the Institute of Computing here in Campinas, São Paulo, Brazil, and the Pontifical Catholic University in Rio de Janeiro, PUC-Rio, the Institute of Informatics, Department of Informatics there. And we created this series of talks last year to foster research in computer science and other areas. And this is called Connection Rio Campinas, Rio Campinas Conexão Rio Campinas. And today we have the pleasure to have Professor Rick Szeliski here with us today. He's going to talk about a decade in computer vision. As many of you know, he is the author of a very important book called Computer Vision. And many of you probably have studied this book when you attended grad school. And it's a pleasure for us to have Rick today with us. I had the honor to meet Rick back in 2011 when I went to Microsoft. And then I reached out to him and said, yeah, would you accept kindly to give us a talk? And he kindly accepted. It's a pleasure to have him here today with us. Rick is an affiliate professor at the University of Washington, and he's a member of the National Academy of Engineering and a fellow of ACM and IEEE. Rick has done pioneering research in the fields of Bayesian methods for computer vision, image-based modeling, image-based rendering, and computational photography, which lie in the intersection of vision and computer graphics. His research on phototourism, photosynth, and hyperlapse are exciting examples of the promise of large-scale image and video-based rendering. And I guess much of that he's going to talk about today with us. So Rick, thank you once again for your time. Normally we stay about 40-45 minutes in talk, and then we go for discussions. Then normally it takes like 25 minutes, 30 minutes. It's up to you in terms of discussion. So thank you very much. The stage is yours.
Okay, thank you very much. Then I'm going to share my slides there. Okay, can everyone see that now?
Yes.
Okay, great. So thank you so much, Anderson, Professor Rocha, for inviting me. And yeah, this is going to be a fun talk. It's the first time I've given exactly this talk. Lately, for the last few years, I've been giving invited tutorials on novel view synthesis, which is one way of describing image-based rendering, because that has a lot to do with taking one or more photographs and then generating new views. So I'm somewhat basing the talk on that. But I also thought it'd be a lot of fun to just look at the last 10 years, because the computer vision field has changed so dramatically, for example, just the number of people who are now going to conferences, and also in the kinds of techniques we're using. And I felt like I'm in a good position to talk about this because I just redid my computer vision book. So the reason I wrote the computer vision book was that I started teaching classes in this area. So I've for a long time gone to both SIGGRAPH and the main vision conferences. And I was invited to teach a tutorial on computer vision techniques for graphics, which back in the early 90s, the two fields were still fairly separate. But I taught these classes, and then Steve Seitz at the University of Washington invited me to co-teach a larger class, a multi-week course on this topic back in 2001. We had a lot of fun doing that. I've really enjoyed co-teaching classes with other faculty. And in 2005, we decided to teach basically a complete computer vision course. So not just about the vision that's used for graphics, but also the vision that's used for recognition and robotics and other things like that. So we developed this curriculum, and it's been quite popular. Our slides have always been online, so other professors often use them. But for some crazy reason, I decided that I wanted to actually write a book about this. I was having a lot of fun teaching this, and I want to share this information with people. So back in 2005, I started writing the first edition of my book, and it took me 5 years to finish it up. So it was a lot of work, but I was very satisfied with that. And then about 6 years later, or I guess 8 years later, in 2018, I really thought it was time to update it because the field had changed so much, and the way it was being taught had really changed. So in some ways, the main point of this talk, or the main material I'm going to communicate with you, is exactly how the field has changed. And a lot of you who are younger graduate students who haven't been doing, vision for several decades, like Professor Rocha, you've only known vision the way it's taught now, which is a lot about deep learning and so on. So I want to give you a slightly broader perspective and tell you which things have changed and why they've changed. So like I said, the first edition of the book came out in 2010 and was a snapshot of the field at the time. The book is kind of leans towards the researchy side in that I cite a lot of the most recent work, and I go fairly quickly over a lot of topics. So in many ways, it's better if you're going to approach the book or our course to have also taken a foundational course in computer graphics and a foundational course in image processing. But with the second edition that came out, actually it came out in print just a few months ago. It's been out online since last year. A lot of things have changed. So even though the graphics look fairly similar, what is on the front page of the book, this was a snapshot from our photo tourism project, which is very much focused on image-based rendering, which has been my main topic. But for the new book, I decided to put a snapshot of the latest work in image recognition, since the field has really had dramatic improvement in that area. So if you look at the table of contents for the first edition, it follows a very classic paradigm that dates all the way back to Marr and others in the late 70s, where you build up vision as a series of building blocks, which have to do with processing pixels, then extracting features, maybe extracting some 3D geometry and segmenting things, and then thinking of recognition as being the highest level process. And in the human visual system, there is this idea of low-level visual processes, which just help you to attend to fast-moving objects, and high-level visual processing, like reasoning or doing mental rotation. So it was a little bit structured like that. If you look at the second edition, what's changed a lot, the biggest change is that I introduced a chapter on deep learning, and I decided to deliberately put it in early. I could have sort of taught all of the classical material and then introduced deep learning near the end because it's a recent technique, but it's so widely used. It's essentially now used in all of the other topics that follow, that I decided it had to basically be introduced, and it's at the foundational level. In other words, if you need to understand basic image processing and pixel filtering and things like that. You also need to understand about optimization, and but deep learning is so pervasive now and so useful that it's taught as a foundational mathematical and algorithmic technique. And then I decided to move recognition up, partially because this is the main topic that students are interested in. So at the University of Washington, when we teach our course, we ask the students to do a final project, and about a third of the way through the class, we want the students to get started on it. And since many students want to work on recognition, I thought, why not introduce it? There's a story where now recognition can be done without really understanding things like motion estimation or 3D geometry. It's not necessary for most of the recognition tasks. So it moved up early. Some of the other things that changed in the book, some of the things that were added were like SLAM, Simultaneous, Localization, and Mapping, which had existed as sort of a branch of structure for motion, but really came into their own as things that now are in all the self-driving cars and self-flying drones and in your phone. So I added that topic. I added monocular depth estimation, which is depth estimation from a single image, which really didn't work 10 years ago. And in the chapter on image-based rendering, one of the newest, most exciting things, which is an area that I currently work in, is neural rendering. So these are some of the new things that have happened, and this is where I'm going to focus a lot of my talk today. Since it's a live Zoom call, if people have questions, please feel free to interrupt me. And if you raise your hand in the Zoom call, I may not see it. So you should either just open your mic and ask a question, or if Anderson wants to monitor the chat, he can do that, but you can ask questions as you go along. So as I mentioned, the sort of old classical formulation of computer vision was something where you started with pixels and you did some image processing, and then you did some feature detection, maybe some segmentation, and then you built up a 3D model, and then that would help you do recognition. With the advent of deep learning, all of that's been sort of turned around, where often you will go directly from the pixels through a bit of image processing to the deep learning. And a deep learning pipeline can learn essentially the image processing functions to do end to end. And then you can go directly to recognition if you want to. But deep learning is also useful for other tasks, like it's now used, as the dominant technique for motion estimation. It's used as the main technique for depth estimation. So it's used everywhere, although it's not necessarily the best choice of technique for all applications. So I'll have a little bit to say about that. So in particular, here's what I want to cover in my talk. And I do see there's a little red chat icon, but rather than opening that up, I'll let Anderson deal with it. So I'm going to talk a little bit about—
I can monitor it here. Don't worry.
Okay, good. Thank you. I'll talk a little bit about the history of computer vision, but this will just be sort of a cartoon sketch of what it looks like. Oh, hello, Luis. And then I will talk about deep learning and why it sort of suddenly became important and what can be done. Then I'll talk about recognition and the really, really dramatic breakthroughs. This is the part of computer vision that's seen the biggest advance. I'll talk about computational photography because it's been one of my favorite topics, but also the really neat thing about computational photography is now that everyone carries it in your pocket. Whether you want to or not, your smartphone has computational photography algorithms running in your pocket, which is really dramatic because 20 years ago, we couldn't even imagine such a thing. Another thing that you also have on your phone is augmented reality. Maybe you don't use it because you don't really need to put 3D objects into your room, but it's there, right? And it's closely related to other technologies. So I'll talk a bit about that. It's an exciting field, and it also basically is enabling all of the self-driving or autonomous vehicle work. Then I'll talk about the other sort of major topic in my research career, which is image-based and neural rendering now, as it's called, right? So the little blue picture is from our phototourism project back in the mid-2000s, and the little animated waterfall that was created from a single still image is some of my latest research. And then at the end, the last topic I want to cover is this idea of deep learning versus classical vision, because this question comes up. There are some students who are entering the field now, because of their courses and what they're reading, may believe that every problem should only be tackled with deep learning, that fundamentally it is a mistake to not use deep learning because the deep learning pipeline learns how to do everything the best. But that's not true. And sometimes it's a little bit oversold. So I think that'll be an interesting topic near the end. Hopefully I can have a good, vigorous discussion around this topic with the faculty and the graduate students who have an opinion. So let me get started. Okay. So first of all, what is computer vision? I'm going to assume that most of the audience here either is already doing computer vision or at least is doing computer graphics. I would have to give a very different talk if this was to a general computer science audience, but hopefully those of you who don't have vision and are looking at this talk series as a way to learn about it will still get something out of it. You can start by looking at human vision. And of course, this slide doesn't do it justice. There's a lot that's known about animate vision by tracing biological pathways. There's also a lot that's known about human vision doing what's called psychophysics, which is experimental experiments with people. But these are just some of the fun optical illusions. If you look at my book, this is a figure taken. A lot of these figures are taken from my book. There are a couple of URLs which will take you to web pages where you can just spend hours looking at optical illusions. But some of the common ones are, why does the arrow on top look shorter than the arrow on the bottom, even though the line is the same? Why does the square called A look darker than the square called B, even though if you just looked at the pixel values, they're exactly the same? The Herman Grid illusion doesn't look like it's much of an illusion, but if you move your eyes around, there'll be little flashing flashing black dots. And the one on the right is fun. Can you count how many red X's there are in the left image? Okay, you should know, right? You should have been able to answer right away. Can you count how many red X's there are in the right image? No, you can't, because I moved the image away too fast, right? It takes you many, many seconds to count all the red X's, and there are good reasons for that. So vision is now very widely used. It's used in a lot of industrial applications like robot inspection. Computer vision is what's now called medical image processing, but when your MRI and CAT scans are processed, there's vision going on to do some of the initial diagnosis. It's used for, this is an old application of convolutional neural nets for digit recognition. So, your letters that you send through the post office are scanned with algorithms. And of course, there are things like self-driving cars and photogrammetry. So a lot of sort of industrial applications, but also a lot of consumer applications. So the panoramic mode in your cell phone camera is based on research that we did in the early 2000s, and that has slowly gotten faster and now integrated into your camera. The same with the image B there, which is taking multiple exposures to get higher dynamic range or to remove blur. The slide C is image morphing. I can't remember, but this may actually be taken from a paper that Luis Velho, Professor Velho had written. I don't remember. But even though you might say, oh, image morphing is a commercial application because it's used by the movie industry, there are a lot of real-time face effects that you can do on your phone now that basically rely on that kind of technology. And the last one at the bottom here is augmented reality, where as you're moving around in the world, even if you're not wearing special glasses, on your phone, you can get directions as to where to go, or you can insert virtual objects. So there's a lot of fun applications. Okay, so the history itself, there's a timeline, and I'm not going to spend time on this. There's too many things to read. If you're interested, it's a lot more fun to open up my book and read about this. But as a cartoon, here's kind of what things looked like in the mid-70s when I first joined the field. There were people like Professor David Marr, who basically thought that you analyze people by breaking them up into parts, right? Or the way to recognize a face is to think of it as an elastic network of eyes and noses and mouths. The way you figure out what a 3D shape is by reasoning which edges are 3D edges and which ones are smooth inside edges. Or the way to analyze an image is what's called intrinsic images, which is to separate the shadows from the texture and things like that. Diagram E is a little hard to understand, but it was one of the early stereo matching algorithms. Diagram F is some early work on optical flow. So a lot of these topics started being done in the 1970s. In the 80s, they got a lot better. We started doing some graphics applications like merging two images or determining the shape of a 3D object by looking at the shading on the surface. Determining things like 3D motion, or the first range scanners became available, right? They were expensive, heavy, power hungry laser scanners, but you were able to back then already scan things like cultural artifacts, old temples, and put together 3D models. In the 1990s, we started seeing some good structure for motion work, which is now what has evolved into SLAM. Stereo algorithms got better. Stereo got applied to complete 3D models. We saw some good work on face tracking. Diagram E is segmentation. So back in the 1990s, you said, here's a photo of a cow on a field. Can you separate the cow from the grass, right? And the sky. And that was the quality of the results we got. It's not that impressive by today's standards, but people were working on it. And we also started having our first successes with things like face recognition. So the 2000s, which is when I finished writing my book in 2010. So this would have been some of the newer work I was writing about, were things like image-based rendering and image-based modeling. Computational photography, you could now digitally enhance dark regions and tone down super bright regions. You could turn images into texture, and you could recognize objects, some objects, like you could recognize motorcycles and airplanes and people. But it was very much based on this idea of bottom-up features. So maybe you had a wheel detector, and then you put it together and you decide this was a motorcycle. And segmentation was getting better. You know, this is an attempt to segment a baseball player from a photograph, but you can see that you're still missing some of the arms and the feet. And now for the new stuff. So these are all pieces of work that were published in the last 10 years, right? Diagram A is a subset of the supervision deep neural network, which really was the start of the deep learning era, because it was the first time that a deep network outperformed a classical technique on a general image recognition problem. B is kind of the state of the art now, where you can turn these deep networks onto a photograph, and it will identify all of the people, all of the surfboards. It'll basically tell you where everything is in an image and actually outline all the pixels. So you actually get an exact segmentation of each of the objects. You can also do very highly accurate human body pose estimation that includes not just the body, but also the hands and the face. You can take range scanners, which became popular with the Microsoft Kinect for gaming applications. You can do a range scan of a person, even though they're moving as you're scanning. And I already mentioned augmented reality. Picture F is a screenshot from the Skydio self-navigating drone that basically can follow someone by reconstructing a real-time 3D model of the world and flying in such a way as to avoid all the trees. So that's kind of a tour of the old stuff. A lot of you may not remember, and some of the newer things. So as I mentioned before, I'm going to focus this talk on deep learning and recognition. I'll talk about computational photography, partially because it's one of my top areas, but also partially because it's now available in your pocket. So it's like an example of vision that really works and is used by millions of people. I'll talk a little bit about SLAM and augmented reality, mostly because they're fun. And then I'll talk about image-based rendering, where I've done a lot of work, and close with a little bit on neural rendering. So why don't I get started? Okay, any questions so far? Okay, so let's look at deep learning. Now, I don't have an easy way to do this, but maybe Anderson can help me. If people listening to the talk have already taken a class in deep learning, can you please use your little, I forget where it is on your Zoom call, but if you could raise your hand, and then
Reactions.
Anderson can tell me if it's roughly the majority of the class. I'd just love to know.
You can go directly to vote in reactions, and you can go to the list of participants and put a hand up or a thumb.
Okay. Yeah, so I see that there are 48 participants. So Anderson, when they're finished voting, you can tell me what percentage of students have already done deep learning, okay? Because I'm assuming that most students that have taken a vision class in the last 4 years have already been taught about this, right? So I'm going to go rather quickly, but I guess what I want to explain for the audience is not what deep learning is, but why it became so popular and so dominant about 7 years ago. So, the idea with learning is you collect a large data set of images, and then you train, and then once you finish training, then you can basically do your prediction, your classification or something, right? So you collect lots of inputs, you collect lots of labels or outputs, you do the supervised learning. And then once you've done all of that work, which typically takes a lot longer, then you can take a new image and give the output, right? The output maybe is a complete identification of all the objects in the image, but it could also be something like a 3D depth map, right? So the traditional pipelines in computer vision were something like take the pixels, build some features, then based on these features, write an algorithm using Computer Science 101 and output something like where is the object and how is it oriented, right? We started doing machine learning in earnest in about the 2000s. So by then what we'd have is these handcrafted features like something old school called SIFT. And then the machine learning algorithm would decide how to put SIFT detections, which might be erroneous, into something like an identification of, is this a motorcycle? And if so, where is it? And the deep learning revolution was basically that you don't even learn the features now. You just put in pixels, you put in the labels, and over time, one very uniform architecture, which has to do with, for example, with the deep pipelines, the deep convolutional pipelines, it's just a combination of local convolutions and nonlinearity, sometimes used in a pyramid or double pyramid, will give you what you want, right? So this is sort of how the field has changed. You've probably taken classes on this. For what it's worth, I really love Andrew Glasner's book. It is actually meant for someone who isn't even a computer science major, because it'll lead you through all the concepts and let you do a little bit of programming with some very simple examples. The reason I like the deep dive into deep learning book is it comes with a complete website of exercises that you can do. So if you like learning by basically doing program snippets as you go along, so you don't wait until you finish a chapter and then you have to do a programming task, you can read along, and there's all of this skeleton code, which is a wonderful way to learn things. Now, of course, good classes are also doing that. So if you have access to a high quality course, that's just as good. And in terms of courses, if you're going to go on the web and try to find a course, my favorite is the one that is being taught by Justin Johnson, because it focuses on deep learning for computer vision. Now, he didn't develop this course on his own. This was when he was a graduate student at the university at Stanford. Alex Kaipati and Fei Li, and I believe Justin was the third one, co-developed the course. And since he's moved to the University of Michigan, he's continued up revising the class with all of the latest stuff. So that's what I would recommend. Okay, so why did deep learning happen, right? What happened? Well, deep learning wasn't invented in 2013, right? When I started my graduate studies at Carnegie Mellon University back in 1983, Jeff Hinton was already doing deep neural networks, and he and Rumelhart and McClellan invented backpropagation around 1985. So it's been around for ages. And the algorithm was already doing something useful. It was producing a state-of-the-art handwritten letter recognizer back in 1998. So if you ask Jan LeCun, they'll say, oh yeah, deep learning has been a great idea. It's been really working well since the 1990s, right? But for a lot of the computer vision community, they would say, yes, but it only works on digits. It only works on letters. It can't really do something like explain what's in an image, right? And the big breakthrough was this supervision deep neural network that was published in 2012 at CVPR. And the reason it was a breakthrough was that it actually outperformed all of the other vision techniques by a significant margin, right? So the tall blue bars are what's the error rate of the algorithm, and by the year. So in 2010, we were still at an error rate of 28%. In a year, they were able to basically drop it by 3%. And then the supervision algorithm, which came out in 2012, basically dropped the error rate by a whole almost 10%. And this was truly dramatic decrease. And each year after that, there were really strong improvements. So what happened was that, the networks kept getting better. They also kept getting deeper, which is going in a direction different than human vision. Animate vision, by tracing how many neural connections there are, you can show that our animate biological vision system probably doesn't go more than about 20 layers or so. And because it has to be fast enough to do basic things like avoid, fast things coming at you. But numerically, it kept getting better, but it kept getting better on a particular data set, which was the ImageNet data set that itself was very important for getting this level of performance. And if you look at the rightmost bar, this is how humans perform. And it's not because humans are bad, but it's because humans might be challenged if they were asked to give the difference between a macaque monkey and some other kind of chimpanzee, right? So humans only have so much knowledge, and the computers got to the point where they could memorize things better than the average human, right? So this is the main reason. And this kind of explosion not only was in terms of deep layer depth and performance, but also in terms of capacity and computes. So the thing to take away from this diagram is probably just the size of the circles, which is how many megabytes of memory, of parameters are there. You have to have 100 million parameters to tune up some of these big networks. And the amount of computation, the number of floating point operations per pixel just kept growing astronomically. So really, and the big breakthrough I forgot to mention was that supervision was trained and run on a graphical processing unit, a GPU. So now to train the newest networks, whether they are computer vision networks or these large language models, take days of server farms to compute. So it does take a lot of compute. Although, as you'll see, some of these things can then be turned around and optimized to run on your phone. Another important topic is this self-supervised learning, where rather than gathering all of the labeled data, you can play these really interesting tricks. Like if you ask a network to colorize an image, to take a black and white image of some flowers and a butterfly and colorize it correctly, as a side effect of that, the network has to, or it seems to, learn a lot about objects and their identities. And so you can do a lot of sort of pre-training, basically have most of the training network done with data that is extremely easy and cheap to gather. Now, one of the things you can do with deep learning is not just label objects, but you can also manipulate images. So for those of you who work in graphics, this is really fun, right? You can do something like take a street map and create a hallucinated 3D model, right? You can take something like the sketch of an object and turn it into a color photograph, right? You can take a picture of a bunch of horses and turn them into zebras, right? So from the graphics side, this is a lot of fun. The image on the right, the semantic image pyramid, was published in 2020, right as I was wrapping up the writing of the second edition. And I love it because it shows that there's this deep layering of networks. You can think of it as an image pyramid, where as you go up the pyramid, the semantics get higher level. So you're working at a more abstract concept. So if you make changes higher up in the pyramid and then have it reconstruct an image, it will preserve certain ideas like, oh, this is a waterfall, but the appearance will change a lot, right? So at the very low level, you can change things like basic color and some fine texture detail. But at the high level, it seems to encode very high level concepts. And you can also use it for a lot of classical computer vision, which were being done with either filtering or these optimization techniques like Markov random fields. So for example, you can do segmentation much better. You can do better feature detection. Pretty much all of the denoising super resolution techniques now use deep imaging, right? You can do optical flow. And it turns out that even though you're using a deep network, it's put together using a lot of the tricks that were learned in the previous 20 years on optical flow research. So you're basically just replacing certain parts inside the overall algorithm with learned components, and that makes everything work better. You can do stereo matching, or you can even do something like, take a color image and hallucinate how far objects are at a very accurate thing. This one-shot 3D photography is a project that was done in our group at Facebook, and I'll mention it a little bit later in the talk. Okay, so let's move on to main topic number 2, which is recognition. And I'm going to go through this very quickly. Again, this is not a tutorial, it's just kind of a snapshot of how quickly things have changed and what have been the most exciting changes, right? So again, I'm borrowing some of the slides from this class. So 2 figures from the 2010 and the 2020 book, right? And what's changed is if you sort of start on the right in the middle with figure E, we can now do really accurate object naming and delineation. Not only can we delineate the objects, but we can actually lift them into 3D. So you have full 3D models of people tracking in video. And you can actually, now they've sort of married computer vision and language technology, so you can have written descriptions of different parts of an image, right? And the most recent examples from DALL-E 2 from OpenAI, where you can tell it to create a make-believe painting, are just amazing. So you should definitely go check that out. It's DALL-E2. And you can go on their website and see all the amazing examples of what's being done. Recognition is really a series of different problems, right? The classic ImageNet task was to just say, what is in this picture? The more classic segmentation task was to say, tell me what each of these pixels is. Is it cat-ish or is it grass-ish? There's also the problem of detection, which is how many animals are there and where are they? And then the most challenging problem is instance segmentation, which is basically where are the objects and which pixels go with which object, right? So all of these have been studied separately. And, you know, and they're covered in the chapter. So I'm not going to spend time on this, but they all map to different sections of the chapter, right? Another important topic has been image data sets, right? Without ImageNet, we never would have had a data set for the supervision deep neural network to train on. So that was a very important component. But eventually these data sets get saturated, right? The performance tails off, so you need better data sets. So this is the Common Objects in Context, which is a data set which actually decided to do the object labeling at the pixel level and say, this is the new challenge we should be working on. It's not just enough to name the objects in the image, right? We can do better. And so this is semantic segmentation, right? Which basically says label each pixel with what it is, right? But it doesn't ask you to identify that there are two cows, right? As long as you label each pixel in a cow as cow, you're done, right? And you can do this with deep neural networks, just like if you're trying to label a whole image, what you do is you basically ask the image to not just produce one number at the end, but you use sort of an inverted pyramid where you go down to a very narrow bottleneck and then you go back up. And essentially what this image is doing is it's running a series of little local stamps in multiple layers with lots of nonlinearities, and it's learning how to do that kind of thing, right? The object detection task is interesting because it's more higher level, right? You can't just run a single network. It actually has to decide on how many answers it's going to give. And for each answer, it has to give the four corners, right? So it's not just a simple, deep, uniform neural network all the way through. And there's been a really fast evolution in this. It's just amazing. You start with something like sliding window approaches, and then you have various region proposals. All of these slides can be found in the lectures by Justin Johnson. And then you have these region CNN, followed by a fast RCNN, and then even faster RCNN. So there's been this incredible progress. And I don't have time today, but it's just wonderful not only to learn about the topic, but to see how clever people are in each year saying, well, this part is still kind of slow, so how are we going to replace it, right? And so it has multiple stages, and the stages are responsible for breaking up the image into hypotheses, into parts, and then running other things on top of those parts. You know, other people, like some of the students at the University of Washington, have said, well, do we really need multiple stages? So they have something called a single shot detector. And it turns out the single shot detectors are indeed much faster, but they're not quite as accurate, right? So there's things like this. And in general, you can take this idea of having a neural network and redefine what it's trying to do. So instead of saying, just tell me where the object is, you can then run a pixel classifier inside each box and end up with the breakthrough paper on instance segmentation, which is mask RCNN. But you don't have to stop there. If you have labeling training data, which basically we've taken people's pictures of people and have labeled different body parts and their 3D shape, you can use that as training data. And then you have these networks like dense pose, which goes from an image to an articulated pose of each object, of each body part in an image, right? Or you can even take an image and turn it into a 3D model, right? So I think that's all I want to say about recognition. You know, it's a very deep topic. Again, I hope a lot of you are studying this area, but there's been wonderful, just amazing progress. It's amazing some of the sheer innovations that have happened here, right? This is a hand-drawn diagram by Ross Gershik, who has been among the most influential people to publish in this area, where he was just trying to explain how all of these networks, mostly to explain to himself, how all of these region CNNs and fast RCNN and the single box, detectors all go together, right? And how they've evolved. So it's been fun to watch this evolution. All right, let me see. I've been talking for a little under 40 minutes. So I will probably skip some of the latter parts of the talk, like on neural rendering, and I can get back to them during questions. But let me cover some of the next few topics and then skip something near the end. So computational photography, is a word for the kind of image processing that takes in multiple images and produces a better, more beautiful photo, right? So it takes multiple exposures and creates a single photo. So we've been doing image stitching since the late 1990s. This is work I did with Harry Shum at Microsoft. Other work we did at Microsoft for removing double images, duplicate or moving people. And it's made its way into various box products, desktop products, and mobile products. So that now basically, this is one of the success stories of computer vision, right? What was a research topic in the mid-1990s is now something that is such an essential part of your phone that you don't even ask, does it have a panoramic mode? Does it automatically take multiple exposures to give you better images? It's like there isn't even an HDR mode because it's just turned on by default, right? Some of the work we did in high dynamic range was not just putting together light and dark pixels, but actually lining them up, right? So if the subject is moving, then you have to use optical flow to line up the pixels before you merge them together. And that's used in a lot of the modern pipelines, like this HDR Plus pipeline from Google, where you take a burst of images and then you do lining up, and then you have to still do what's called tone mapping to get each different part exposed the right way. And this just all happens in a fraction of a second on your phone, right? Image-based rendering is another fun area that has evolved a lot. It's still looking for a widespread big hit the way computational photography is. But the basic idea is that we're going to use computer vision and computer graphics together to create more realistic 3D models. So some of our early work was this paper called Lumograph back again in the mid-1990s. And what we're trying to do with image-based rendering is to model all of these complex image effects, like the parallax, how pixels move as you move the camera, right? Occlusions, things hiding each other, right? Translucency, so you can see through some things like dirty windows. Refraction, a glass vase will bend the light going through it. Objects have highlights, right? Shiny parts on objects, and windows have reflections, right? Surface light fields, I'm going to skip this part, but basically this is an interesting paper that was introduced in 2000 that is now sort of being rediscovered by a lot of the new neural rendering papers. So some of the most recent work is using these ideas of basically describing the light coming out of a surface rather than the light coming into a camera. One of the fun projects we did was called Virtual Viewpoint Video, which was our attempt in a small research group to reproduce something like the bullet time effect from the Matrix movie, which was shot with dozens of cameras with just a small number of cameras. And we basically took the cameras and we applied multi-view stereo matching to create a 3D model to go with each of the color images. And people are working on these things now. For example, this is a project at Google where now instead of having a rail of cameras, they have a whole hemisphere of cameras, right? And the basic observation was that you want to take a color image and split it up into not just the depth, but also what are called fuzzy boundaries, alpha-matic boundaries, in order to get the best realism. So, in some of these ideas of taking color images and depth maps, in this case, taking depth maps using a range camera are being used by Project Starline, which if you've seen from Google is a way of building a better 3D video conferencing system. think I'll skip 360 videos. Basically, we worked on this in the early 2000s. And now basically you can buy 360 cameras and put them on your helmet or hold them in your hand and upload them to places like Facebook. You know, if you want to sort of look at things on 360, if you upload your 360 photos to Google Photos, you can also look at them there. And there are very high-end systems like the one we built at Facebook. One of the projects I was, most excited about working during my career was this photo tourism project, where you could take collections of images from the web. Back before social media sites like Facebook, there was Flickr, where you could upload your images if you want to share them with the world. And we would take these images and build a 3D model. And then what we could do is basically, I'll back this up. Here, you could basically fly around in this scene, and to look at the photographs, you could basically point at a camera and say, show me what was seen from that viewpoint. Or you could focus on a particular part of the scene and then say, take me to a better photograph of that, right? So, this was a very sort of creative, inspiring combination of computer vision and computer graphics. Google had a follow-on project called Photo Tours. And then we did something called PhotoSip at Microsoft. One last thing I'll show in this sort of line of image-based rendering and computational photography is this 3D photograph project we did at Facebook, where you could take a bunch of images, create a depth map, and then do visual effects. And this was released on Facebook, where you can basically take a photograph and create a 3D mesh from it. And then as you're looking at it on the phone, just like when you rotate your phone around, the panorama swings around. When you look at a 3D photo on Facebook, as you rotate your phone, it rotates in 3D, right? So there's a paper that explains this in SIGGRAPH. And basically a lot of different computer vision components have to be put together. And we wanted it all to run on the phone. So we had to make really fast neural networks that ran on a phone, like a neural network that in a quarter of a second convert a color image into a depth image, right? And then it can fill in the missing pieces of the background, right, in half a second, and it can create a 3D mesh, right? So it's been amazing to see all of these techniques, which sometimes are still run for training purposes on a server farm for hours. Once the models are trained, you can run some of these deep neural networks in just a second or two on your phone. Okay, I'll just show this topic because I think it's a fun thing that's happened in the last 10 years, which is where this simultaneous localization and mapping, which was a term developed in the robotics community to describe what happens when you put a robot into a mine where you want it to explore the mine and simultaneously localize itself so it knows where it is and map the area, right? There's been a lot of progress. The biggest breakthrough was to basically combine this with what's called visual inertial odometry, which means use the IMU that you can put on a robot, but the IMU, it turned out, was there in your smartphone because Apple decided that they wanted to have a smartphone where you could play little tilty games. You could do a maze on your phone. So they added an IMU, and now that's used as part of the augmented reality things. So SLAM is used in autonomous navigation. Another kind of autonomous navigation is for flying drones. Beautiful work from Skydio. I'd recommend looking at the talk that Jeffrey Cross gave. That's linked to from my book. And you can do augmented reality, right? So there are all these applications now where you can walk around in an airport and it'll tell you where you should be walking, or you can put fun virtual objects in your scene. You can put in new furniture into your room, right? So this has been a big breakthrough, a lot of fundamental mathematical improvements, plus great hardware work. And for this kind of augmented reality, to be able to hide objects, not only do you have to be able to tell where the camera is, but you actually have to build a detailed 3D model so you can hide things behind trees and tables and things like that. And someday we're going to have lightweight AR glasses, right? So I think this is gosh, I can't remember. Oh, this is the latest version of HoloLens, right? So we already have AR glasses. They just turn out to be so heavy that you have to like crank them onto your head with a band, right? But someday, soon, hopefully, there'll be lightweight things, maybe heavier than this, but we'll see a lot more applications when they become much more portable. Okay. I think because I've been talking for well over 40 minutes, I'm going to skip neural rendering. We can come back to that if we want to later, but there's been a tremendous amount of advances, wonderful tutorials online. I actually did some fun research projects with a bunch of students on this, but I'd rather just jump to the last topic I was going to cover, which is deep learning versus classical approaches, right? And this is not a finished story. I don't want to say, oh, no, the way we used to do it is better. But there have been some very interesting papers that point out the limitations of some of the deep learning work, right? So if you like the topic, go back to ICCV 2021 and see if there are videos for this panel. A lot of very famous computer vision people, including Andrew Davison, who did a lot of the SLAM work, and Jitendra Malik, who's one of the great old figures in our field. Some of the papers I found very telling was this one by a group which basically showed that this kind of deep network that directly predicts where the camera is from the pixels is just a bad idea. It can, if you basically take a bunch of photos walking down a hallway, and then you give it a new photo and say, where am I? It's great at telling you where you are between any two photos. But if you moved a couple of feet to the left, it has no idea because it's not the way it was trained. It never had to learn about 3D geometry. So there are some places where people, because they choose the data sets and the test sets in a way, make it seem like deep learning is working much better than previous techniques, but sometimes it doesn't when you look carefully, right? There's this great lecture by Sri Nayar on first principles of computer vision, where he goes over a lot of the classical techniques. And in the introductory lecture, he says that, why don't you use deep learning everywhere? And he has some good reasons, like, well, you have to capture a lot of training data. But his last one is the most compelling reason to learn things from first principles is curiosity. What makes humans is the innate desire to know why things work the way they do, right? And so this means not totally ignoring the physics of how pictures are formed and that, right? This is another paper that's very interesting. There are a lot of papers that'll say, give me a photo, I'll build a 3D model. It turns out that because they test these things on a very small data set, like just motorcycles and airplanes and chairs, essentially what the network learns to do is just to recognize the object and then stretch it. And that's all it's doing. So it's not really building a general 3D model. It's actually kind of just recognizing and stretching, right? And these are some examples from that. But there are definitely cases where it helps a lot. So this work out of Mark Polife's group, if you can recognize what's building and what's tree and what's grass, you do a much better job just getting a 3D model, right? And it's amazing that you can do single image depth reconstruction. But again, depending on your training data, if you train on Kitty and then you put a refrigerator in the middle of the street because it's never seen refrigerators in the middle of the street, it will say there's nothing there and drive right through it, right? So you have to be very careful about, you've got training data. If your example isn't part of the training data, you're on shaky ground, right? But you can counter this by basically using very heterogeneous data sets. So the very nice work from Vladlen Colton's group, where they use a lot of different training data to come up with a much nicer way to get depth inference. And they have a way of telling how brittle the different networks are. Okay. Yep. So I'm going to wrap up. I know I've talked for more than 40 minutes, but these are just some general observations. So, I think that students should study alternatives to deep learning, right? If you can actually come up with a mathematical model, a true mathematical model is something that is a scientific fact and doesn't depend on the limitations of your training data. So there's a lot of reasons to try to model the world if you can. And if you use limited data sets, then you're on shaky ground when you come up with something that's outside those data sets. But deep networks can also be very fast, so they should definitely be used, just with caution. This is advice I often give to my students, which is have a plan for what you hope your research will produce. And if you have that, you can probably write an abstract that at least states what you're hoping the paper will have demonstrated, right? If you can have some sort of a visual demo that people will really like sort of a 3D fly-through, keep frequent notes and updates. A lot of students come into my weekly meetings and say, well, let me start telling you what I did last week. And they're just not very effective because it's like retelling the same story. We can't remember what we discussed last week. So I'm a big believer in keeping notes and trying to do lots of small experiments to see what's really working. If you just sort of build a system, try it on an existing data set, and you get a certain number, you don't really understand what it does, or which parts are really meaningful and which ones aren't. So there's a summary. Basically, I've tried to give you, I hope you found this interesting, but kind of a history of computer vision, a little bit about the big changes in learning and recognition, a couple of topics that have been near and dear to my heart, and a little bit of a teaser about deep versus classical computer vision. And of course, none of this would have been possible without all the wonderful people I've had the pleasure to work with over the years. So I'm going to stop and happy to take questions and open up the discussion.
Thank you very much, Rick, for the excellent talk.
Thank you.
And it's nice to see how things evolved, because it kind of coincides with when I did my undergrad and I saw all of this evolution, and it's very nice to see also these discussions at the end. I will start with one sentence that you mentioned right in the beginning, recognition without understanding things. And right. I'm gonna put this in the context. Many students and many researchers actually, nowadays, they enter the field of AI or machine learning or vision, and they do things without understanding things. And this is kind of easy with deep learning. You just need some input and you have some output. Of course, we know from experience that garbage in, garbage out.
Right.
But how do you see these? How do you see a student that comes to your door and says, I want to do deep learning, I want to do this way? And you have the whole discussion to convince the student that this is not the way to do it. How do you see this going on?
Right. It's a great question. There are different reasons why students want to do deep learning, right? If they're just getting into the field, understanding the technique by actually programming a network and developing new things is a very good technique to have under your belt, right? So if they've never done deep learning before and they are saying, I want to learn deep learning, I think that's great. On the job market, it's almost an essential now that you understand how to do it, right? If they're saying, I want to do deep learning because I'm sure this is the correct approach, then you sort of have to guide them to alternative approaches, right? And say, look, read this older paper that doesn't use deep learning and explain to me why you think deep learning will do better. Or better yet, if it's a student and you're paying their salary, you can say, you have to download this old code and prove to me that it actually works better, right? So if you believe they're making a mistake, then the onus is on them to prove that this is a good approach, right? And if they say, I only want to do deep learning, then you can say that's fine, but there's also the question of, am I as an advisor interested in this topic, right? So I would say the more you know about where the limitations are of deep learning, and the more you can point those out to the student, the more likely it is that they'll look at alternative things, right?
Yeah, I agree. Another thing is, when I was an undergrad and entering also my grad school, the comment was that in vision, you don't have anything that works. And at least it's like, I discussed this a lot with my advisor here in Brazil, Professor Sean Goldenstein, and also in the US with Terence Bolt. Probably you know Terence Bolt from Colorado Springs.
Yeah.
And yeah, it's the truth. Nothing works in vision, but like in the last years, you can see that a lot of things are working, and they are industry, in the industry, they are products. And now
That's
the
right.
comment is the contrary. Vision is over. Vision is solved, right? So
Right.
this is the other side of the coin.
That's
So
right.
how do you see this? For you, what do you think is really solved, I would say, in vision? And could you point out one or two problems that you see as very challenging yet in vision and that you don't see like any solution in the next 5 years?
Sure, sure. That's a great question. Before I answer that question, I'll just point out that if you decide, instead of studying computer vision, that you really like civil engineering because you like the idea of being behind buildings that don't fall down and look elegant. I mean, look elegant is more the architect, but if you're a civil engineering professor and a student comes in and says, I don't want to work on civil engineering, it's solved. Well, you can say, well, that's funny. We know it's solved, right? This is engineering. You're just going to learn how to do it well. And there's going to be incremental improvements, and we're going to invent new things like, pre-stressed concrete and so on, right? So there is a part of computer vision that's an engineering field, and whether it's solved or not isn't relevant, right? As a matter of fact, if you are more of an engineer, you should be happy that it's solved because it means you can go out and build lots of cool stuff, right? If you happen to be more of the research bent, and you really only want to work on things that are unsolved because you love that challenge or because you like having your name on papers, then that's a different question, right? And again, I sort of focused in this talk on what was solved precisely because I came of age at a time when so little was working. So it's really, just heartwarming to see how much stuff now works and is useful, right? But in general, I would say that the things that are unsolved are, fundamentally, the general AI problem still isn't solved, right? Even though we can now identify pixels, right? We can do that in these closed worlds, which is whatever the data set was trained on, right? But in general, if you now, for example, if you have pictures of, let's say, scanning electron microscope pictures, right? If you've seen what they look like, they're sort of these gray shaded bumpy things, right? And you ask the person how many sphere-like things are there, we can make some sense of that. I don't know if a training algorithm that doesn't have that kind of training data could do it, right? So the general recognition problem that has to do with intelligence and common sense reasoning, it would be hard to argue that even though the algorithm can label pixels, we're still working on things like, here's a photograph, what's going to happen next, right? If I showed you a photograph of me holding my phone and ask the question, what happens if I remove my thumb, right? And the phone's going to fall down, that kind of common sense physics. Now, you could say that's not computer vision, right? But I think as it gets to higher levels, that's still not solved, right? From an engineering perspective, there's always power issues, right? So if you want something to run well for a long time on a mobile device, then getting things that are more energy efficient are still an issue. So those are some of the thoughts, but it's actually a great question. I haven't been asked it recently, so I don't have really good answers, but I think I'm gonna, in the next week or two, I'll think about it more so that I can have that as a backup slide.
Very good, thank you. I've been thinking about this because, as I said, when I started, nothing worked, and now they say everything is like ready to go. So, but it's not true. So,
yeah.
Another thing that I have in mind here is a subject that's very dear to me, and it bears a little bit in vision and also machine learning, is forensics. So when you need to check if a video or an image is fake or not, or to identify like things like deep fakes, and I've done a lot of research in the field of forensics over the years.
Yeah.
And you said, and of course, as you also have a background in computer graphics, when you talk to a person in vision and computer graphics, of course, they want the best algorithm to generate content and to complete an image. But of course, you have the dark side of the thing. You have like people using this kind of thing to create content to like blackmail other people. So How do you see this? Because it seems that we are on the brink of being able to create such realistic content. Like when you see at things, it's so photorealistic that it seems real.
Right.
But it also represents a possible problem to democracy and other things. How do you see this going on? Because I imagine that in 5 years, pretty much everything could be created, like digitally. And where could we be? Where could we be? Because forensics will be like in on the downside, because the generators will be much better. So how do you see this?
It's not a problem I've worked on. I'll tell you, my personal opinion is pessimistic on being able to continue to detect these things. I mean, we went through a transition, although for a variety of reasons, where we used to have radio and there'd be radio interviews, and eventually we went to television and people would rather see a talking head than hear something. Although there are still lots of wonderful podcasts where you can listen to fascinating people for ages. But if a newspaper reporter basically now said, here's my source for an interview, or I have a scoop, and here's the audio recording, people would sort of question, like, well, is it really an audio recording, or did somebody manufacture it, right? So yeah, audio recordings are still admissible in court sometimes, but it's because you really trust the person doing it, right? It's a police person who has a reputation, and so you have to trust their recording, right? But people basically, when you hear somebody speaking in the voice, now famous actors will imitate other actors for fun, and we all think it's super funny because we see the face of one person talking like someone else. But basically, audio, the ability to fake audio, I mean, even humans being able to fake someone else, has just happened a long time ago, right? And I think, I'm glad there are people like you and Hani Farid working on digital forensics. Hopefully it will help. But I'm fundamentally pessimistic. At some point, we're just going to have to trust what's called the provenance. Do you really trust this organization or so on, that they just try to maintain safeguards against tampering? But if it's a random video on YouTube or Twitter, it's like, I don't really, from a random person, I personally don't trust it. But, maybe the majority of the world does. It's like, oh my gosh, this is horrible. Let's go do something because I saw this video, right?
Yep, exactly. It's Daniel Kahneman's like, what you see is all there is.
Yeah, right.
Okay, I have some questions also here. My PhD student, Gabriel, is asking this. Specifically, you can answer specifically in terms of vision, but it also applies to other areas. What do you think about self-supervised learning? Do you think it's like the next big thing? Do you think we can reach a point where deep learning models can directly learn from data with minimal or no human intervention, and at the same time deal with possible biases?
Great question. Wonderful question. First of all, I'm not an expert in this area, but given that, I'm happy to offer an opinion, right? And there are really two questions there, right? Can algorithms learn from a lot of unlabeled data, right? And will it help with the bias problem, right? So can they learn from unlabeled data? Absolutely. I'm very excited about self-supervised. There are some people like Jan LeCun who sort of say this is the next most important thing. I think there are a lot of important things, but in the process of writing my book, I was just really delighted to see how clever people have been by saying, we take some images and we artificially create this task, and it appears, we don't understand why, but it appears that solving this task forces the network to come up with a fairly good internal representation of how the world is structured, right? So I've just been delighted by a lot of the self-supervised examples, and I expect to see lots more, right? Can it remove biases? That's such a tough question, right? I mean, you might, on one hand, you could say, well, yes, if you sample from all the images that are on the web of people, you will probably have a somewhat representative distribution, let's say, across ethnicity, right? Not necessarily, because there's still income level disparities and so on, but at least you can get millions of images of people from every, ethnic group and more gender balance and things like that. So yes, there's those chances, but even the sampling of data in the wild has a lot to do with socio-demographic things, right?
Yes.
So I would say on that one, I'm mildly optimistic that there might be less bias, certainly less bias than what a researcher 10 years ago would do when they said, go get me some experimental subjects. And the experimental subjects were graduate students in their lab. So you had this incredible bias towards, validation by graduate student, right? So yes, no, in general, the less supervision you need, probably the bigger the chances that, first of all, the biggest advantage is you will just have much more training data. So any effects that are due to insufficient data will start being mitigated.
Another thing that when you compare the old way that you do vision and the recent way, let's say, is that pretty much understand everything that you did. You did the math and you could understand where this point would be and everything else. And
that's right.
With deep learning, it's pretty hard to understand. Of course, we have advances in the last years in these terms of explainability,
right.
But it's also difficult to understand what's going on. So what's your take on this? We have on one side the advantage of understanding things, but sometimes it doesn't scale in terms of recognition. On the other, we have the deep learning derived things that we are seeing that work well, but they don't have explainability. How do you see these things going together so you can get the best of both worlds and having explainability?
Yeah. It would be great. I think it's a topic we should focus on, that it's sort of, in my mind, it's kind of more interesting to have explainable networks than to have networks that somehow improve the performance by a few percentage points, right? And there are definitely areas where the judgment involved seems pretty subjective, like let's say credit rating, right? Or something like that, which isn't even computer vision, right? Where those sorts of increasing transparency on decisions is much more important than with an image sharpening algorithm, right? If an image sharpening algorithm kind of sometimes introduces a little bit of artificial texture here, less likely that bad things will happen, right? Whereas, for example, with a self-driving car, it could be worse, right? So the importance is there, but I hope that more people focus on this, right? It's just not my area of research, so I don't have very well-informed opinions. I'm not sure who you've had talk in your seminar series, but to get someone who actually works on recognition, like Ross Gershik or Jan LeCun or someone like that, you would get much more informed views on this kind of a topic.
Thanks a lot. Another one here from my student, Rafael. Awesome talk. Google announced today the immersive view for Google Maps, which is based on NeRF and rendered 3D-like models from landmarks as well as indoor spaces like restaurants and museums. In your view, what are some of the challenges to scale techniques like phototourism, LAM, and neural rendering to the global scale?
It's a great question. I saw the announcement go by, but I didn't actually read the technical details to realize that it was using NeRF, which is very exciting because I love that work, right? At a strictly technical point of view, the way that NeRF was originally formulated as a mapping from a bounded volume to color values doesn't by itself scale to an unbounded volume like a whole city, right? Now, there are ways you can dice up the city into smaller parts, and there's an upcoming CVPR paper on, I think they're called urban NeRFs or something like that, where you divide up the world into blocks. The phototourism was, in some ways, it's a really old thing, but it had the benefit that it was very local in that all the system was trying to do was give you plausible transitions between neighboring images. The SLAM problem essentially scales very well, because if you have an aerial map, you can geo-register everything, and basically being able to geolocate every camera and build a sparse point cloud-like model is definitely doable. And that's partially what underlies things like, Google 3D or Google Earth, whatever you want to call it, right? Is that there was enough money to fly enough airplanes and run enough computers to basically build a low resolution 3D model. And the immersive world basically increases the resolution for certain cities, right? But strictly speaking, from a technical point of view, I don't think the vanilla original NeRF scales up, but I believe that groups like that who are working on neural rendering are actively working on a scaling problem. I've seen some recent publications, both on scaling and on compute times, because the reconstruction is very slow, and some of the rendering algorithms are either slow or very memory intensive. So my prediction, having worked in this area, is we're going to see a lot of progress. And ultimately, the scaling issues may come down to an economic factor, just like I love Google Street View, but not every rural street. Actually, it's amazing how much of the world they have scanned. But at some point, the economics means that not the inside of every person's home will not be scanned for good reasons, for privacy reasons, right? But maybe even the inside of every restaurant will not be scanned because the economics doesn't dictate the need for that, right?
Awesome. Back when you and Noah and others were developing photosynth, I discussed it a lot with him, and but I never asked him, aside the computational hardships that you had back then when you did it, what was the main challenge in terms of science when you did photosynth and phototourism?
Right. I think there were two different threads in that work, right? One was scaling and reliability of the computer vision algorithms. So the structure from motion and 3D reconstruction, the ability to do that with unconstrained photo collections had already been demonstrated by Zisserman and oh gosh, I forget, Szeliski, I think, the Where Were My Photos Taken paper. So people had already shown that you could take arbitrary collections of photos and build a 3D model, but they were very small scale demonstrations. So we sort of scaled that up to a whole city, right? And those were classical computer vision challenges, like how do you do structure for motion on such large data sets? And our group eventually, when other people like Samir Agarwal joined, and then the work by Mark Polyphys and Jan-Michael Fromm. So there was a lot of technical work that enabled the scaling up, right? The other main thread was just the artistic side, or the graphic side, as you might want to call it, which is how do you basically render this thing in a way that looks pleasing, but not confusing, not dizzying. It's not totally realistic, but you want it to still give a sense of motion and those kinds of things. And I think there we did a lot of trial and error and came up with some things that, were interesting. There were little details like the fact that when you were outside the boundary of a photo, we just showed little line sketches. That was a non-photorealistic idea that David Salison, who was, another professor at University of Washington, suggested, right? So, and so I think there's going to be that combination. There's one line of work that believes the best you can do is to always come up with something that's photorealistic. As soon as you create the illusion that you're actually there, it's a real video camera moving around, then you're done. But that kind of begs the question of photorealistic when, like when it's raining, when it's sunny. And of course, there's been very nice work that Noah and others have done on basically doing image-based rendering and changing the time of day and the weather and things like that, right? So I think to answer your question, two of the challenges were fundamental computer vision challenges having to do with 3D modeling. And the second one were, if not challenges, there were delightful discoveries about the rendering side and how to do that well.
So last question. What would you say or give us advice for a student starting today in vision? And what do you think of the field for the next 10 years?
Sure. And again, a student starting in vision can mean many different things. It could be an undergraduate who would like to finish a degree and is really loves software engineering and wants to work on some aspect of software engineering that includes computer vision, right? Then it's a question of sort of training yourself in the right series of techniques and developing maybe a sub-interest. So are you the kind of vision person who wants to go work on self-driving cars? Are you the kind of vision, is your vision interest more in recognizing large image data sets or creating better photo editors, right? That kind of thing. So they're developing your mathematical techniques, of course, developing your collaboration skills, your software engineering skills, and maybe to a little extent deciding which particular kind of thing you're interested in, right? Because even within something, sorry that I keep bringing back civil engineering, but my father was a civil engineer, right? Within civil engineering, you're going to decide whether you are more interested in building buildings or if you love water flow and you want to work on sewage and drainage systems, right? So even within computer vision, there's different applications and knowing, although as a well-trained undergraduate, you can move around a lot of these applications, right? So that's the answer to the undergraduate. Let's assume the graduate student is staying in graduate school and not getting a nice, well-paying job because they really love research, right? And they want to keep publishing, right? Then the question is, partially, do you think you want an academic career? And you will discover that during graduate school because you will have to teach classes and you'll get to know whether you enjoy that, right? Or are you happy with industrial research? If you're going to do industrial research, having that engineering bent of what do you want to build that is really exciting that you can tell your uncle about and explain it to him. You know, that's always driven me, is I love building things. And so you'll find that there's students like that. And then you should help them focus on learning the right techniques that help you build engineering things, right? Then there are the students who just love mathematics, and you can kind of point them towards the aspects that have more math, right? And the one question that I've carefully avoided answering, which is, Professor Szeliski, you've been doing this for so long. What is the research topic that I should choose that is going to have amazing impact when I solve it, but can be done in 3 years, right? Because that's the golden question, right? That everyone wants to know, and no one knows. You sort of, as you become a mature researcher, you develop the taste for saying, you know, this looks promising. I think I have a better idea on how to do it, and so on. But I think it's really futile to try to predict as you're doing research what the next most exciting thing is. I think you should follow topics that feel intrinsically interesting to you. And personally, this isn't advice for everyone, but personally have some demonstrated utility. So aren't just solving problems that only work on paper if you assume a bunch of things that don't occur in practice, right? But that's just my own research taste. Of course, mathematicians are very valuable and they do a lot of that work, which is, let's assume the following 2 hypotheses hold. Look at this amazing stuff, right?
Excellent. I completely agree with that, because this is what I tell my students. I love to see things that we research, and when they go to practice, it's amazing. So Rick, thank you very much for your time again. It was amazing. And for everyone here, thank you also for your presence. We will put this video on YouTube later on, so help us spread the word. It was amazing to talk to Rick today. Thank you, Rick. Stay safe.
Okay. Thank you, everyone. Thanks. Bye.
Thank you. Bye-bye.